All right, folks, let's get you guys up and running for this last set of the action potential lecture slides. So pull up the one about axons are classified into three groups, about the diameter, type A, B, and C. You got to quickly address what the heck that means. Wait. It's not big enough yet.
No.
All right. All right, so the last little bit about this, we went through how you form and make an action potential with the sequential opening and closing of voltage-gated sodium channels at the initial segment, in which case every time you make action potentials, it only happens in the nodes of Rand-Pierre segment, not in the internode regions. We know that we can determine how fast we can make new action potentials, or how many we can send per second because of refractory period. If you think about the absolute part, the amount of time which you can never send another action potential, and there's 1 millisecond. How many milliseconds in a second? 1,000, which means that a neuron can send no more than 1,000 action potentials per second of time. That's the fastest you can possibly create them, because you have that limiting thing known as the absolute refractory period that limits the ability to make a new action potential. We talked about other classifications of organizing neurons, besides structural, besides functional, in terms of sensory, interneuron, and motor. We also have kind of a functional in terms of what kind of neurotransmitter do you release. Are you one that releases acetylcholine? Then you're thought of as a cholinergic neuron. When you go into, I don't know about dental hygiene, but definitely PT and nursing programs, you'll have cholinergic type drugs. That's what you know that's dealing with probably acetylcholine, and then the specific types of receptors would be nicotinic or muscarinics. Adrenergic drugs work on adrenergic neurons, those neurons that release norepinephrine, epinephrine, which means you need an adrenergic category of receptors, more specifically alphas and betas. They're discovering new alphas and new betas, so there's more than what we actually have on our lecture sheet. You'll learn about the specific alphas and betas individually, but we did make kind of a general classification that alpha ones and beta ones are what? More than just nothingness. They're excitatory, right? And alpha 2s and beta 2s could be inhibitory. We'll be a little more specific tonight with the sympathetic nervous system with our new set of lecture notes. What we didn't get to is yet another way of classifying neurons. And that's based upon their diameter, which relates to their speed of conduction or their velocity. Now, they gave you one general rule, which I had you guys attached to, which is when chemicals land on proteins, proteins change their shape, like neurotransmitters landing on receptors. When chemicals come off of proteins, proteins change their shape as well. There's also a thing about the diameter of a structure. The larger the diameter of any structure, the faster, the easier things move through them, the less resistance there is. The smaller the diameter, then the more resistance, the slower things tend to move through them. Your type A fibers are the largest in diameter we have. They're very large in diameter, and because of that idea, that means things will flow through much faster, and there's very less resistance compared to smaller axons. So type A's are larger in diameter, and because they're larger, they also must be myelinated. So type A's are large in diameter, heavily myelinated, and then the speed at which action potentials travel. It may not sound like a lot to you. It's 268 miles an hour. But if you think about it, if I'm standing right here at this coffee cup, and we'll pick on Brandon since you just came in, and Brandon's going to drive his modified 1973 Camaro by me at 268 miles an hour. If you sneeze, you're going to miss it. So If I'm only this long as a neuron, and I'm traveling at 268 miles an hour, that's pretty damn fast, actually. Any kind of sensory information is going to travel along those neurons, like sensory for pain, for pressure. Because you want that information to get to some interpretive center quite quickly. Type B fibers are smaller in diameter than A's, but they're bigger than C's. And they're still myelinated. So B's are smaller than A's, bigger than C's, and still myelinated. So by that general rule, since they're smaller in diameter, they have to travel slower. All right? They're going to travel about 40 miles an hour. That's a lot slower than 268 miles an hour. Most of your viscera work by type B fibers, internal organs talking to the brain and other parts of your internal anatomy. And look at the general trend, right? A's are the biggest, B's are smaller than A's. What do you think C's are going to be? They're smaller than B's. They're the smallest. And they are unmyelinated. They get a double bad whammy. Very small in diameter, unmyelinated. They travel at 2 miles an hour. That is remarkably slow compared to 268 miles an hour. Why would you want information to go at either 268 miles an hour or as slow as 2 miles an hour? Probably to do two things. One, be able to respond to your environment. Like we talked about in the lab about reflexes. If you step on a tap, or if, for example, let's do it this way. I think I told you the story, I may have been getting my quarters mixed up. I was walking down the stairs of my apartment. I had concrete stairs onto a rough gravel sidewalk, and I thought there was one more additional step, and I started to fall. The ability to recognize that I'm falling visually and proprioceptively because of my joints. I want that information to be responsible at traveling at 268 miles an hour so I can begin a reflex response of beginning to brace myself. When I hit the ground, I was quite aware of hitting the ground. I was also quite aware of the fact that it did not hurt at all, not in the slightest. When I picked myself up, I was more concerned about my phone than I was my palm. Looked at my palms and I realized, oh wow, this is really freaking cool. It's like I took a cheese grater and just grated the palms of my hand. What was cool was, A, it didn't hurt, B, it wasn't bleeding, and C, I knew that it was operating on type C fibers. The pain hadn't reached me yet. But I knew in the next couple of seconds I was going to begin to feel it. And that was the delayed response. Those of you that ever put your hands in hot water under the sink, right, and you pull your hands away and it's still getting hotter, even though your hand is no longer under the hot water, that is again because of type C. Pain fibers send signals via type C pathways. What's more important is removing yourself from the danger rather than recognizing the pain. So you got A's, large diameter, heavily myelinated. B's, smaller in diameter, still myelinated. C's, very small and narrow, and unmyelinated. 268, 40, and 2. And then this is just to give you a picture of really how crowded a soma can actually be. They have counted as many as 50,000 synapses on one neuron soma. That's a lot of cross-communication. And if you think about it, if you looked at the idea of EPSPs and IPSPs, right, excitatory and inhibitory, those are the only two signals we've got, really. It's like zeros and ones. So it's either a yes message or a no message. So this one neuron getting all these different synapses, it's looking for the majority. If I get more stimulatory signals, I'm going to create a signal. If I get more inhibitory, I'm going to shut down and not send an action potential. That's all that it is a yes and no. But I want you to realize that it can be really, 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 really crowded on that soma. It isn't just one or two synapses. And that's the last little bit. for those guys, I believe. Yes, it is. All right, now we got to have a little bit of fun, but also look at the function of the brain, not sensory pathways, but the functions of the brain. Before we get into that, I need to do one thing first. All right, so hopefully we've all learned the various lobes of the brain, the various central and lateral sulcuses. We know that there are also things called cortexes that respond to very specific stimuli, like the occipital lobe, the visual cortex for vision. The temporal lobe has the auditory cortex for hearing. We have a precentral gyrus and a postcentral gyrus. That is their anatomical name. Their functional name, however, is a little bit different, not much. They're known as the primary motor cortex. This is where voluntary skeletal muscle activity will start from. The blue one, there's two ways to think of it. You can either call it the primary sensory cortex, or some books call it the primary somatosensory cortex. It's the same thing. Somato is referring to the body. So it's either the primary somatosensory or just the primary sensory. In this cortex are neurons that will let you know what part of the body is experiencing a stimulus. What part of the body is experiencing a stimulus. Little heads up on how to answer the question on page 3. If I were to ask you what is the function of the postcentral gyrus, what is the function of the postcentral gyrus? Do not say its function is the somatosensory cortex. All you've really done is renamed it. I want to know, what does it do, right? It lets you know what part of the body is currently experiencing some type of stimulus. All right, so let's talk about those two major cortexes. There's a really cool cell type found in the primary motor cortex called pyramidal cells. They're like an upside-down pyramid. They have a tremendous number of dendrites. So they can get lots of information from other neighboring neurons. In terms of what are those types of stimulus that we know your body is experiencing, what the somatosensory cortex truly does is measure the amount of temperature, pressure, pain, and vibration you're currently experiencing. And we're going to look at the mapping of the neurons that are sensing all of these.
And the pyramidal cells are both supposed
No, they're just in motor neurons. There are no pyramidal cells in the somatosensory cortex.
not in the postcentral.
Right, that's why it's only under the pyramidal, under the primary motor. Now, there's going to be a general path that we're going to look at. Any stimulus you get, for the most part, any stimulus, has to go from a sensory neuron to your thalamus. From the thalamus, it goes to the somatosensory or sensory cortex. So almost all of your stimulus is passed through the thalamus. My tongue is not cooperating. So all sensory information passes through the thalamus, except for one. We're not quite sure why this is true, but olfactory, the sense of smell, that sensory pathway does not go through the thalamus. Why is that significant? We'll mention later tonight that there is a part of your brain known as the RAS. Anybody heard of the RAS? It's called the reticular activating system. RAS is involved in arousal, not sexual, but conscious arousal, waking you up. So I could walk up to you, I could shake you, right? That'd be touch and vibration. You would wake up, which means those signals pass through the thalamus. I could yell at you, hey, wake up! And it's going to pass through the thalamus. Why do you guys have smoke alarms? And why? Exactly. Smell will not wake you up. Olfactory does not pass through the thalamus. Now, why that's true, we haven't figured that out yet. But that's why you have an auditory smoke alarm, because that will help wake you up. But the sense of smell won't. This is what's known as a homunculus map. We're looking at, I did the sensory motor, we did the motor first. So there up in the top is my precentral gyrus. This would be your longitudinal fissure, and down here would be the edge of your lateral sulcus. What they've done is they've mapped out what part of the body goes to that part of the cortex. Remember, we're looking at the cortex. They just made it blue this time. And they realized that my face, the neurons that receive signals when you touch the pharynx or the tongue or the lips, jaw, and face, they're found over here. And correspondingly, the neurons that receive signals from my hand and thumb are found over here. My shoulder and hips are found over here. My toes are right down here. The easiest way to think about this is pretend you're standing in the longitudinal fissure, wiggle your toes down, and then just simply lay your body over the parietal lobe down to the lateral sulcus. It gives you a general idea of what part of the body is corresponding to what region of the cortex. And that's what I want you to get, is the general idea. Do not memorize the actual order of body parts. But if you have a study guide question, that's for the general layout of neurons for the somatomotor cortex. Now, the cool thing is that if I could take this neuron over here for your thumb, if I could detach it and move it over here to your toe, when you think you're moving your toe, or your thumb, excuse me, you're actually going to move your toe. Because the signals start from this part of your cortex. The size of the word or cartoon caricature of the body part is in relation to how many neurons are dedicated to that part of the body. We have an awful lot for the face, an awful lot for the hands, which means we must need really fine control over that part of the body. Look how big the tongue is. I mean, why do we need so many motor control neurons for my tongue? All it does is let me swallow food, right? Helps you with speech, be able to form words. And there's subtle little shapes your tongue has to make to be able to form speech. So I need very good control over that very strong muscle in my body. The same thing happens with your sensory cortex. Brandon?
So is that on both sides of the brain?
Yes, left and right.
Left and right?
Exactly.
And so is it a mirror image? So right now,
Yeah, it is. Yeah, it would be. So if this is going to be, let's say, the anatomical right side, so we're looking at this, let's say this one right here, right? Because we're curving in this direction, then this one would be the same way.
Okay. And then it just controls the other side.
Right, now since you just mentioned that, remember you have on your list for the medulla the decussations, which is the crossover? So in a sense, if we're looking at where my red light's pointing to, and this is the right side of the brain, they're going to come down the spinal cord and cross over and actually function on the left side of my body with them. Remember, the right side of the brain controls the left side of the body, and the left side of the brain controls the right side of the body. Sensory is the same thing, right? Just realize that there's nothing different in terms of the pattern of orientation. And again, the size of the cartoon caricature is in reference to how many neurons I need dedicated to that part of my body. So you've got a lot of neurons coming in sending signals to the tongue and to the lips and the teeth and such, right? A lot to the hands. I mean, overall, that's a lot of area, a lot of cortex just for my hand itself. And again, if I had a neuron coming up this way that went to, let's say, your nose, if I could take this neuron that's coming up and remove it from the cortex and bring it over here to your wrist, then if I touch your actual nose, you're going to feel it on the wrist. All these neurons do is saying, this part of my body is being touched. The perception of what it is not happening at the cortex. All this is saying is, if I touch my wrist, then those neurons are being activated. All it says is, your wrist is being touched. It's going to be the association area that tells you what that stimulus was. You're going to associate a memory to that stimulus. Okay? So all this does is saying that this is a part of your body that is experiencing some kind of stimulus. Maybe pressure, maybe temperature, maybe vibration. But all it is saying is something is happening in my wrist. That's the job of the cortexes. No matter what kind of cortex it is, auditory, visual, olfactory, gustatory, all it says is we are experiencing something. It's the association area, so I'll let you know exactly what that was. We're going to give you some analogies of these. So think about, the movie Matrix and the little quote from Morpheus, right? What is real? How do you define real? If you're talking about what you can feel, what you can smell, what you can taste, then real is simply electrical signals interpreted by the brain. Every stimulus you experience has to have an association area with it. Has to have a memory of what that thing was. That's what you accumulate during childhood. You know what rough is. Mom says, feel this nice smooth kitty? You learn that that's what smooth is, right? I mean, I could take you as a newborn baby and really screw you up, right? How sour sugar is, how sweet sriracha sauce is, right? Because you're learning what that stimulus is, and your brain will make a memory of that's what sour is, that's what rough is, that's what pretty is, that's what ugly is, and even that will vary to a certain degree.
But there's none of it on that,
But you have to, all the tongue is saying is that, for example, if you're getting sour, it's through the hydrogen ions crossing through a chemical gated channel. But why am I giving the name sour? That's where the association area comes in. Right? Anything you name as sweet, sour, bitter, soft, rough, hot, cold, rough, smooth, heavy, light, is because your brain has learned to make that label to that stimulus. You're not pre-programmed to what heavy is.
So the primary motor, if this is just, if primary
Somatosensory.
somatosensory is just the interpretation of a stimulus.
Right.
And the primary motor context is the,
That is just sending a message to a muscle to make it contract.
so that is the, that might be the translation.
No, remember, that sensory is pressure. I don't need to have any muscular response to pressure. Does that make sense?
But the motors make your tongue.
Right.
Like,
The motors make the skeletal muscles contract.
okay. So the somatosensory is really the interpretation of the stimulus.
Of a stimulus.
Not the motor. So.
Exactly.
Okay.
So in other words, if I went over here and I took a wire whisk and I destroyed all of those neurons, then you're not going to be able to move your arm because I've destroyed them. All right? Now, the way they figured this out in the old days, especially this one, was you're in a car accident back in the 1950s and 60s. We're going to fix your brain, and then we're going to have you sign a waiver saying, once we're done fixing and we saved your life, can we screw around for a little while and poke around, literally? And you're going to be conscious. You're not going to be unconscious when they do this. They're going to take a probe, maybe a little electrode, and they're going to stimulate that part of your cerebral cortex and say, what do you experience? Tell me what you are feeling. And if they said you heard little birds chirping, then they're going to record, I hear little birds chirping. If you record, well, I feel something on my face, and they go over here and they poke this part and say, well, I'm feeling something on my thumb, or now you're poking my tongue. They map the brain out that way in the old days. Now we can put something on your tongue and use an MRI or a PET scan and do it that way. But since the brain is receiving sensory signals, right? It receives signals for temperature, for pressure, for pain, for touch, but the brain itself has no pain receptors. Doing surgery on the brain has no pain at all because it has no pain receptors. It interprets it. It does not have any pain sensors. What's going to hurt is cutting through the skin of the bone. That'll hurt. But once you're in there, you're not going to feel a single thing. You might experience something, but you won't feel any pain. Well, how does this all work? If we keep in mind that every cortex has a special sensory job, right? A visual sensory, auditory, right? A gustatory, an auditory sensory system, then every one of those also has an association area. Now, the job of the association area, if I get my tongue to work here, is to associate a memory to that stimulus. To associate a memory to that stimulus. That means learning has to take place. Attaching a memory to that stimulus. Let's give you some examples. You guys got to play around. Got to play along. My tongue is working very well tonight. I want you to close your eyes. Don't cheat. I'm going to play you some music. I want you to not look, because the name's probably going to show up on YouTube. I want you to tell me, if you can, what it is you're hearing. All right? So, close your eyes. Don't cheat. They're cheating. I'm checking. Hang on. Got to launch the silly, slow Windows 10 Explorer. Hang on. We're still launching. This does not count.
We asked for Seattle. Can you let us perhaps...
All right, now, keep your eyes closed. Let's see if you recognize this piece of music. Come on. All right, can you name that? All right, you open your eyes now for a moment. Beethoven's Fifth. All right, so what's the point of this? You had to have air pressure waves go to your ear to activate a neuron that sends a neuron signal, an action potential, to your auditory cortex. All it is hearing is turn on, turn off, turn on, turn off, turn on, turn off, turn on, turn off of action potentials. Kind of like Morse code. The pattern of the turn on, turn off, you have learned as being the pattern of Beethoven's Fifth. But all it is a pattern of how long the signal is on, how long the signal is off, and what is the pattern of yes, no, yes, no, yes, no, yes, no. The association area is like a voyeur in a sense. It's like watching the pattern of signals going, that pattern I have learned is Beethoven's Fifth.
So are people who are really good at like recognizing faces or recognizing sounds, they just have like a more active association area?
Yes, they probably have a more, either a greater density of neurons or more astrocytes to make connections between the neurons, and more maybe of those annexonic neurons that can connect this one to that one and go, oh, that's this, a lot faster. Now, close your eyes again. Let's try this one. I'm going to find it. Hang on. That's why I love Windows 10. Come on. Now, don't say anything yet. Just yes or no. Can anybody recognize this? Right? If you can't, maybe you need this. Hang on, it's coming.
All along it was a fever.
Maybe you needed a voice to go along with it, right? Which means you needed more association areas. Still the same thing, right? It's a pattern of action potentials. So your brain goes, oh, that's music. It's not a dog barking, not a kid screaming, not John's irritating voice. And then the pattern of the signals with the voice going, oh yeah, okay, now I know what song that is.
Is there someone who does not know the song? Is there someone who does? How are you?
Well, I recognize that it's music,
Right.
and then I start going, okay, I can recognize if you're a music major, the tempo, the harmony, the A flats and C sharps and all, but I have no name for the actual pattern other than it's a nice piece of sound to it. And then you'll learn that that's going to be known as stay.
Okay. Well, like, in terms of the on and off, like, what do you mean by that? Like,
It's just a pattern of, sort of like if someone were no, I can't, it's the same way of doing it. Do you know what the light signaling system that the Navy uses, right? Where they flash the light on and off, it's just a visual Morse code.
Okay.
Imagine every flash you see as an action potential, right? I have a duration of the action potential, how long it lasts for, and then the pattern of 3 longs, 2 shorts, I interpret it as a certain musical sound. And that's what your brain is interpreting what that sound. But you have to learn what that is. You have to learn what a drum sounds like, what a violin sounds like, what a piano key sounds like.
Okay.
And that's the pattern of signals that are happening. Just to see how different it is, you can watch this part. I couldn't resist the first part of this. I'm sorry, just could not resist this first part. We'll get to the more important part. Boy, this is slow.
These tests are pathetic.
Okay. Couldn't resist that part. But let's get to right.
Name an American composer. Bach.
No?
Mr. Sullivan, what kind of music do you like to listen to?
Rock and roll.
You? Anybody here like Johann Sebastian Bach? Other than you? I'll bet all of you, whether you know it or not, already like Johann Sebastian Bach. What's this called? Lover's Concerto. Who wrote it? Voice.
So in case you did not realize, well, we went away. That was the video we just watched in black and white. What Mr. Opus is trying to tell you is that
Wrong. That was Minuet in G, and it was written by Johann Sebastian Bach.
by a slight alteration in tempo, your brain can pick up that slight various alteration. I can barely hear it. My godson, who's a music major, who now teaches in Medford, talks about what's called the ionic pentatonic scale, like whatever the hell that is, dude. But a trained ear can hear the slight subtle differences in the pattern of music. That is how sensitive your brain actually is. And just for little fun whoops and giggles, have you ever noticed the bust that was in the video? That was a bust of Beethoven. They're making the connection that this is actually a piece of Beethoven that's slightly modified, sped up just a little teeny bit. Makes it sound a little bit different, but it's still recognizable because of your association area in your brain. How many of you can reach into your pocket and grab a very specific key without even having to look at it, right? Like, let's see, right now I can grab, so I have the, there we go, the media cabinet key in my hand, right? That's because my somatosensory cortex, my sensory cortex has an association area, and I've learned what metal feels like, I've learned what a round key feels like, and I have learned that the round key is for the media cabinet. That's what all these association areas do. You have to be taught what that is. But you're simply making a memory or associating that stimulus to a particular memory that you stored in your brain.
But you can learn, like, what something feels like without actually touching it, right?
Yes, but that's because you had experience. You have to first know what soft is.
Okay.
You have to know what hard is.
Okay.
And if you don't have that learning experience, then If I try to describe what hard is, you have no context to make the association with, you're gonna be like, what?
But I mean, like if you, I'm trying to think of how to explain this, but if you like just looked at bones, and then later you had to like figure out what a bone was by touching it, but you just looked at them, so you never actually touched it, but you just looked at the angles, and then you went and you knew it, but you know what it was just by, like, could you translate visual information into your association area?
Well, I have a visual association area. Are you saying, can I translate visual into tactile?
Yeah.
As long as I have some context of what rough is, and I look at the greater tuberosity of the femur, I can look at it and go, oh, that's going to be rough when I touch it.
Okay.
But I had to be taught what rough is and what it's going to feel like when I do touch it.
Okay.
So if you are absent of that experience, then you have no construct to make that connection with. Well, we have two other really important association areas. And one of them is known as your speech center, otherwise known as Broca's motor area. And Broca's motor area, the one in yellow up there, is what's going to control your ability to form words. Then, and we're going to get more into this. Over here, you have what's known as the general interpretive area, right? Interpretive, right? To interpret, to make an interpretation. That one is actually more known as Wernicke's area. And it's usually, in most people, on the left-hand side. But it is like Grand Central Station. It's getting lots of input from various cortexes, and it's involved in the interpretation of language, being able to use it and to interpret it. That's both written, tactile, and verbal, and auditory. Not anything is verbal. Now, if it's going to be, for example, for me, it'll be right here on mine. If mine is on my left, and some people it's on the right-hand side. But on the same place, on the opposite hemisphere, is another Wernicke's-like area that applies emotion to language. So you understand the emotional context of communication. So for example, let's say David, you just walked in, and you were kind of farting around. You didn't want to interrupt, but you're kind of just like, okay, I don't want to interrupt. And I looked at you and said, David, take a seat. What are you going to do? You're going to walk in, you're going to sit down, right? Because you understand the emotional context of that sentence. Because your Broca's area works, and your Wernicke's area works. But if you had damage to the opposite side, so for me it would be my right side, he's going to misinterpret that very simple sentence, and he's going to walk over, he's going to pick up and take a seat. He's going to leave with it, because he missed the emotional context. And that's what Wernicke's is all about, is being able to make association and understanding language. It has really two interesting problems with it. If I can find my markers. If it doesn't work very well, in terms of Wernicke's or Broca's, we're going to do each one. We have a problem known as aphasia. And that's the inability to understand language. Because A means without, and aphasia means speech. But it's the inability to understand language. And we have two major groups of aphasia. You have one that's known as fluent. Fluent aphasia. Anybody know what that is? Anybody had psychology or anything? And then we have the other one's going to be non-fluent aphasia. Fluent involves the Wernicke's area. It's damage to Wernicke's. You have the ability of forming words perfectly. Nothing wrong with your pronunciation. But the words come out all screwed up. So for example, you could have what's known as word salad. So let's say normally I would say, David came in, I said, David, it's okay, go ahead and take a seat, sit down, and get your notes out. Now I want to say that to him, I'm going to have a fluent aphasia problem. In my head, I am going to think exactly what I just said. Right? David, come in, it's okay, sit down, take a seat, take your notes out. What actually might come out is going to be notes, see, cubby, purple, whale, tobacco sauce. Bunch of words, all formed correctly, but have no contextual sense whatsoever. That's word salad. All the words are mixed up, not even the same proper words. Now, what's really interesting about aphasia, or the Wernicke's area, is it helps you to understand language. You can have the following possible thing wrong with you. I could say, David, go grab the coffee cup. And he grabs this instead. Or he sits down. They couldn't understand the auditory pathway. So first it's going to go to the auditory cortex. The association area is going to be there. It's going to send a message to the general interpretive center, known as Wernicke's, for language. And there it doesn't make sense. It doesn't know how to understand that signal. But if I wrote it down for him and had him read it instead, he does it perfectly. That's a visual cortex, visual association area, talking to Wernicke's. So you can have things that are known as like word blindness, where you don't understand written language, but you can hear it just fine. You can't read a sentence correctly, but you can hear it just fine. Blind, right, to see.
So we're still talking about fluent.
You're still talking about fluent, yeah, because it's involving the Wernicke's.
But you were saying that if they were to read it, then they would do it just fine. That's what I'm.
No, I thought I said, okay, so let's back up. So if you were to hear it, you can't do it, then that would be involving the auditory pathway, right? That'd be like word deafness, right? If you were to read it, you would do it just fine. But if you couldn't read it, that'd be word blindness. Maybe I just made down the space between the transitions. So if you can hear it, that's okay. You won't be able to read it. If you can't read it, that'll be word blindness. If you can't hear it, it's things like word deafness. Then you have non-fluent, which involves the Broca's. And that, I guess the best analogy is, think about listening to Klingon. Any foreign language, Russian, you know no Russian at all, right? You are unable to form words properly. So what comes out of your mouth is a total mystery to everybody else listening. You, however, know exactly what you're saying, and you get really frustrated. You know, John, I'm sorry I'm late, and kapla comes out of your mouth. You know, I hear kapla, you hear I'm sorry I'm late. And I say, what? And you went, what the hell's wrong with you? You know, I said I'm sorry. I keep hearing kapla. Because your ability to form the words that you need are not working properly. And that's because of Broca's not functioning.
So for both of these, would sign language be a way to communicate then effectively with both aphasia?
As long as you didn't have a visual pathway problem. So what you want to first figure out is why you're not understanding me. Because the hearing pathway isn't working, okay. The reading pathway isn't working, but now the reading is kind of a visual. But they're trying to figure out then,
You can do it where it's touch.
well, you can do it where touch, that's tactile. You have to learn, God, I could never do that, all right, how to do that. But they're trying to figure out, because some people who cannot read can do visual, they can do glossing. So the question is, well, that's both visual pathway. So there's something about the way your brain interprets reading, right? Like when you're little kids, you learn this, right? It's a cat. But you had to learn that that shape was first called a C, that shape is called an A, that shape is called a T. And that might be different than doing a gloss, a pattern of motion, which is interpreted differently than a static image of letters. All right, so general interpretive areas, you've got Wernicke's, involved with the interpretation of language, right? Being able to understand it in an auditory, a visual, or maybe a tactile way. You have two types of.
So this visual, is it just like, you have two in this area? for,
Say that again, I'm sorry?
if there's visual language and auditory, how does it visual, like, if somebody has a learning disability, like dyslexia or something like that, would that be?
Might be part of it, yeah. I mean, it could even be something that, for example, you know what John sounds like?
Yeah.
And so if you listen to my voice, oh, that's John. If you saw a picture of me, you would not be able to name me whatsoever. But if you were, let's say, a blind person and you learned what John's face feels like, you could go, oh, yeah, that's John. Or olfactory, you know, John wore a certain cologne or a certain perfume, a certain cologne, right? So there's a really fun book that deals a lot with this idea about how the brain has to interpret information. If you have time during the break, read Oliver Sacks's The Man Who Mistook His Wife for a Hat. And look at the title, The Man Who Mistook His Wife for a Hat. Right? That was a visual association area faux pas. He thought his wife was his hat. And he tried to put her on his head. You know, yeah, in that sense.
So, how does that happen? Sorry, so.
I don't know how it happened, but just that.
In terms of this, how would we have this?
Oh, so that's not a aphasia for that scenario. That is a association dysfunction.
Okay.
Right? For example, he recognized most of his. There's a story of a music teacher who recognized most students by their voices, but couldn't recognize them by the face at all. So an auditory pathway worked just fine, but a visual facial recognition pathway didn't work well for him at all. There's lots of these little anecdotal stories that he has from his case histories that are in there. Another major interpretive center is the frontal lobe. It's another place of interpreting lots of information, known as the prefrontal cortex. One of its jobs is the idea about the what-if scenario, being able to plan for the future. If you play cards, you're doing a what-if. What if I play the 5 of diamonds? If you play checkers or chess, it's a what. What if I move this way? If you're at a signal light that says don't walk, what if I walk across the street now? Those are all interpreting how fast the car is moving, where are the pieces placed on the board, what is your amount of risk you're willing to partake. We're all about what ifs. Motivation and desire come from the frontal lobe as well. A lot of your anxieties, level of calmness can come from the frontal cortex. And then on the lower part of that, you can have then, of course, Broca's, which is known as the primary speech center, your motor speech, being able to form words properly. Then we get to the next one, which is known as the basal nuclei. Some books might call them basal ganglia. Not a good idea since they're in the central nervous system, but they mean the same thing, right? Basal nuclei are a collection of nuclei within the white matter of the cerebrum. We have a little diagram to show you them. What they're basically involved in is coordinating skeletal muscle movement. They're like the middleman between the primary motor cortex and your cerebellum. The best way to look at them is in a picture here. So if we look at this, right, we're looking at a pretty far deep cross section. You have part of your lateral ventricles here, your septum pellucidum separating those two. You have all these different colored islets of tissue. These 3 are the basal nuclei. The amygdala should not be in here. It's not a part of basal nuclei. But in terms of which one's which, right, you have the caudate nucleus, which is here on this image. Now, depending on where we make the cut, the best thing to think about it is the caudate could also be next to the thalamus. And we're not showing the thalamus here. We will in the next coming slides. This was cut rather deeply into the brain. Then we have this one here, again, closer to the thalamus, is called the globus pallidus. And this collection of nuclei is called the putamen. So we're going to have the putamen, the globus pallidus, and the caudate. These 3 will play a role in coordinating voluntary motor movement and even unconscious motor movement. Think of them as the middleman. You're going to get a signal from your primary motor cortex that you want to move a certain muscle. It has to go through the basal nuclei, talk to the cerebellum, and go back to them, go back to the cerebrum, and then back down your spinal cord. Don't memorize the actual pattern. You don't need to do that. I'm just trying to let you realize that this is kind of a complicated pathway, that these nuclei do play a role in making for nice, smooth, coordinated muscular movement. They sort of tell your brain, oh, you don't need that neuron to fire, so don't send that one down to the muscle. And it makes a nice, more organized motion. If, for example, the globus pallidus does not work properly, doesn't do its inhibiting job, then you can have Parkinson's, or the video about dystonia we looked at. So what they have found is that doing things like deep brain stimulation, by inserting a permanent probe into the globus pallidus, by short-circuiting the short circuit, we can then allow for a more appropriate pattern of muscular signals to go down to the skeletal muscles. But these guys do a lot of cross-talking, and we're not quite sure the actual sequence of events, but we do know these three play a role in coordinating skeletal muscles, and we do know for sure that you can aim at the globus pallidus to help people with Parkinson's, dystonia, and some other skeletal muscle disorders.
So if you're really klutzy, does that mean that something's, I mean, not, I don't want to say not quite right, but that means you have less going on there than someone who's really
I wouldn't say that.
coordinated?
I mean, maybe it is. I haven't read any papers that try to explain why you're klutzy. If you think about this, so I want to pick up this whiteboard marker. All right. First thing is a what if. Prefrontal cortex has to activate. What if you pick that thing up in the following pattern? Okay. Now I got to send a message to my primary motor cortex about what muscles I want to use. It has to then talk to the basal nuclei. As I begin to make my motion, my cerebellum is also saying it has a certain stored sequence of motions that I tend to use for picking things up off the table. So it might be that when I go to pick this up and that I didn't get the pattern of closing my fingers properly. It could be a primary motor issue. It could be the cerebellum was like, I haven't learned which neurons not to fire or which neurons to make sure do fire in the proper sequence. So I guess what I'm trying to say is it's probably between the cerebellum and the basal nuclei, somewhere in there, just not an accurate fine-tuning. So I would be bet that if you just trained yourself, that you would no longer be klutzy in that particular motion or movement.
So just those three are the basic.
Yes, because the amygdala is more involved in primitive emotion and plays a role in your limbic system, not so much basal nuclei. All right. How do I get different parts of my brain to talk to different parts of my brain? I have association areas, I have cortexes, I have basal nuclei. How do they talk to the various parts of your brain? You have several different patterns of interneurons and neurons, axons, running through brain tissue. The first group are known as association fibers. And there are two kinds of association fibers. You have arcuate fibers and you have longitudinal fasciculi. Let's look at a picture because it makes more sense than the actual words. And we'll come back to the last two. This diagram shows you the arcuate fibers, because arcuate means arch. They form a little arch-like shape. They are gyrus to gyrus only, and in the same hemisphere only. So gyrus to gyrus, same hemisphere. They don't go over multiple gyri. So what I mean by that is this. Let's look at the first pattern of arcuate fibers here. See how this gyrus is not sending fibers all the way over to this one. It's not skipping over a gyrus. It's just neighbor to neighbor and that's it. If you're not next to me, then I can't use arcuate fibers. But then I can send a signal from here to here, to there, right? I can go over to here, come down here, go up to there. I can leapfrog my way, but I'm using arcuate fibers to do so. Of course, then you have to ask, why would you have your primary motor cortex talking to your somatosensory in the first place? But if I want to go from a lobe region to a lobe region, or from one part of a lobe to the other part, I can use these very long fibers known as longitudinal fasciculi. Again, they're only in the same hemisphere, but they're more thought of as lobe to lobe parts. So you can do frontal to parietal, you can do frontal to occipital, you can do frontal to temporal. But to do that, I would use these longitudinal fasciculi. But what if you do want to talk from hemisphere to hemisphere, from left side to right side? Then you use the corpus callosum. These are known as commissural tracts. There's two major ones. The big one you guys will learn about called the corpus callosum, and then a little teenier set known as the anterior commissure. So they allow for left and right communication. Well, that gives me gyrus to gyrus, lobe to lobe in the same hemisphere. Hemisphere to hemisphere communication through commissurals. What about brain, top of the brain to the bottom of the brain, or from brain to spinal cord? Then we need projection fibers to up and down in a sense. So here we have our corpus callosum running through here. And here's what I was talking about in terms of where you make our, well, we'll do that in a second, lateral selection. Here's up and down, right? These are projection fibers. You can see there is your diffusation. If we follow these projection tracks, the right side ends up on the left side. And the left side ends up on the right side. So it's projection fibers allow us to do that.
What's the evolution behind why
It's-
it's possible?
It's just the way the brain folds as it's developing. You know, I mean, if I were the all-intelligent being, I would say, why make a place for things to screw up? You know, that's the way the brain folds as it's being developed. There's not a reason for it, it's just more of, oh, that's what happened. Have an idea. Now let's go back to the basic nucleus for a second. All right, this was cut, so if you're looking at me making the slices this way, they made the slices pretty far back, like the posterior third of my brain. But here we realize it's the same pattern, but now you can actually see that they're talking to the thalamus, and there's just the tip of the caudate. But there's your globus pallidus, and there's your putamen. But now they're actually able to see the actual thalamus and your third ventricle, right? Which you could not see in this diagram because of where they made the cut. But you can see the anterior commissure, projection fibers, known as internal capsules, and your corpus callosum. You won't be able to see these at all in any of the brain sections unless you stain them to stand out. Then we have another way of looking at projection fibers coming down, right? Corpus callosum, hemisphere to hemisphere, and anterior commissure, hemisphere to hemisphere. These are more in the frontal lobe, and these are more of the parietal lobe areas. All right, let's do the diencephalon, then we'll give you guys a break. So we know the technical 3 parts, the literal 2 parts to a diencephalon. You have the hypothalamus down here, you have the thalamus here, indicated by the bullseye idea of your intrathalamic adhesion, and then the third unofficial part known as the epithalamus. Most importantly, it's part here called the pineal gland that is just above your superior colliculus. Well, what does all these various parts do? First one is let's do the pineal body. Do the first part, epithalamus. It produces a hormone known as melatonin. And melatonin plays a role in your circadian rhythms. Another word, your day and night cycles. How do you know when it's day? How do you know when it's nighttime? You have a biological clock that's running, and that's based upon your ability to see sunshine. You see sunshine, it goes from your eyes, and it's going to send a message to the pineal body, and it says, hey, it's daytime. In the absence of daylight, you start producing more and more melatonin, which helps to make you feel sleepy, which is why you can go to GNC stores and get melatonin capsules to help you if you don't have regular sleep patterns. If you were to put someone in a completely darkened room, or give them a room with no UVA, UVB sunlight, then their biological clock will slowly get screwed up over time. How many of you have the nice talent of being able to get up in the morning on the same time almost every day without an alarm clock, especially when you want to sleep in, right? That's your biological clock going. I irritate / piss off my friends because we can be out backpacking and they're going to say, oh, I wonder what time it is. And I'll stop and go, should be about 1:20. I'll be off by about a minute or two. That drives them nuts, right? I just have a really sensitive biological clock. But if you don't get the signals from sunlight, then you become off a little bit every single day. It's what's known as free running. And you lose the coordination of daytime and nighttime. And if you work on graveyards, work at night and sleep during the day, you have a really hard time adjusting your proper circadian rhythm.
So people in Alaska, they have a lot more, they have a harder time.
Have a hard time, yes. Naval submariners and submarines had a really hard time being deployed for 3 or 4 months underwater, no sunshine, getting their clocks to be accurate. That's why the Navy put in UVA, UVB lights in submarines these days.
My husband was born and raised in Alaska. He's only been here 2 years. He has a hard time sleeping.
Right, because his brain's been organized into that pattern. He's got a whole new pattern of daylight.
This is based off the sun, so then in the fall, it would be different than say in summer. Or
Right.
In
Yeah.
winter, it'd be different in summer.
Yeah. I mean, how many of you have a hard time? I mean, when we had our longest day, where it gets dark at about 9:45 at night, and you want to go to bed at 10, going, it's still too late for me to go to bed. Your brain says it's daytime, which means you should be awake, right? And in the wintertime, you start getting tired earlier because there's a lack of sunshine. The brain says, oh, it's nighttime. Get your butt in the cave, get away from the bears, and go to sleep. And so even the winter seasons have an effect on your ability to stay awake or to fall asleep.
But then, like, in order to change from like fall moon to summer moon, like,
Right.
like spring to summer, like how would you change? Or like how long would it take to like get to that?
Well, remember, every single day is what? We're longer by 2 minutes, shorter by 1.5 like that. So you have these very little teeny adjustments. Your brain can accommodate that, and it slowly begins to adjust. That takes a while. So it might take a couple of months to switch between fall and winter, or winter and spring. And if I took you out of the dead of winter, put you in the dead of summer, you'd have a little bit of a problem catching up and making rhythm with that. So pineal gland produces melatonin, which is multiplicating rhythms, allows you to keep your normal biological clock running. The other proof for this was people that are born blind have no circadian rhythms. Because how many of you had other physiology classes? Did you guys learn about the eye? Did you do rods and cones for sure? Did you do the new receptors? The non-rod, non-cones? We've learned about a whole new set of photoreceptors whose only job it is to say yes or no, there is light. And people that are born blind don't have them. And so they need sound to use for their circadian rhythm. So you actually have 3 different types of photoreceptors in your eyes. All right, let's give you guys a break. We'll give you a 5-minute break and we'll look at the thalamus and what it does. So I would say, David, it takes several weeks to get adjusted. Only from what I remember hearing about, like when I grew up during the Cold War, you had Minutemen, right? Men who lived in the nuclear bomb silos. They're stationed there for months on end, like half a year at a time. And Navy submariners underwater for long periods of time would take them weeks to get on a normal daily cycle. They're always put on a graveyard first, and then slowly adjusted to a swing shift or a day shift. So it'll probably take you months to go from one thing to the other. But since the day hours slowly change, there's enough for your brain to slowly kind of keep pace. You'll be maybe a little bit behind, but kind of keep track of the rolls. So if you notice now, this is August. So the days are getting a bit shorter. Right? You might find yourself now getting more willing to go to bed at 10 o'clock than you were several weeks ago. Because several weeks ago was lighter at 10 o'clock. Your brain goes, dude, it's nighttime. You go forward for food.
It's an
Right?
exception.
But nighttime there's scary monsters around. And you can't see Bella, you can't see the cave. So you're noticing, instead of realizing what it is. That's what cave rhythm is.
Yes, CO2
And so then this
oxygen,
hormone
CO2
plays a role like serotonin and such.
So
Serotonin
this is like
becomes,
one folder. Substance.
and the more melatonin you have in circulation, then your brain's saying, geez, later in the day, later, now there's enough to trigger you to want to go to sleep.
Potassium.
If you have a hard time thinking, you go to C stores, health food stores, you find melatonin tablets. Well, it helps you go to sleep. It's not like a drug that puts you to sleep.
It helps you because then you're inherited in your way, you don't have less.
Right, because we get to wear off, and you'll get an inhibitory signal from what's called the RAS. It'll send a message to the pineal body, saying, okay, it's time to wake up. Let's end this melatonin pathway for that period of time. And to pick them up.
You have to do your own weekend bullshit. I hope very thoroughly.
So when you're cannabis.
Yeah.
You have one operative, well, two operatives, two columns of operatives, Monday, Tuesday, one column of operatives.
See, I go back and forth, like I'll hold her for half an hour and then I'll go over and help with them.
So we get you unscrewed with word salad, word blindness.
I watched all your videos yesterday, and then I watched one of the top that I watched. That,
I didn't post a video on word keys.
no, I know, I went down to deep dark.
Ah, okay.
All about.
Okay.
No, I, yes.
Yeah, so think of this, if I am to interpret language, it's a word key. If I'm to speak language, it's a broken. And then there are different ways that Wernicke's can have, so it's associationary. You know,
Non-fluent associated program. Fluent associated program.
right, because fluent means I can say the word properly. So pronunciation isn't an issue. Right. Right, so whether, right, if it's written or if it's auditory, tend to be the two major ones. Then they're probably exploring the notion of sign language. So someone who maybe had a hard time understanding communication, probably teach them sign language, and then teach them what it is tactile.
I did sign language in college, but then it was full with a brain.
Mm-hmm. Right.
Totally fine.
Yeah. You know, all kinds. There's even a story in the book where there's a guy that you can walk up and say, "Hi, my name is John. You are Dane. Nice to meet you, Dane. Hi, my name is John. Nice to meet you. Who are you?" And he could not remember anything permanent.
Was that short-term memory loss?
Yep. He remember everything from a certain date on back to his birth almost.
So where does your memory?
Well, it's part of your limbic system, hippocampus. So it kind of follows, you imagine the corpus callosum kind of looping around and getting down under, kind of flanking the thalamus. So it's this loop of tissue that runs right along the thalamus. And it looks like ram's horn, it looks like lateral ventricles actually. But they're a collection of neurons that play a role in emotional context, like the amygdala, memory, short-term, long-term, hippocampus. And so they have, yes, I don't remember what the reason was for this trauma. I don't know if it was psychological or physical. But there's all kinds of little fun stories like that in the book. Well, be careful. As far as I know, there's been no documented case of a truly feral child. No documented case. They're all living as a family, got abandoned somehow, or got separated somehow, but they're not truly feral. Feral will be born in the wild without any parents to raise you. No, they'd be abandoned, neglected, like Annie. under the stairwell, right? Or, Victor of Avio was in 1700s. He was a small boy found in the forest. Well, he had to be raised by somebody, because he had language. He had to learn from somewhere.
The one I was with, it was
So she can't be feral. She's already been raised by people. Right? Now there's a fusion mistreated, all other, but she can't be feral.
But she couldn't,
Right. The idea of boys being raised by wolves, or there's a boy claimed in Thailand to be raised by monkeys. No, they tracked it down over a couple of years and realized that we got separate from his parents. I don't know. There's a lot of those. Well, there's a thing about learning called the critical window of opportunity. So the definition of learning is you need experience, you need outcome, and you need memory. And then there's a window of time where you need to experience that for it to stay with you. So like in the story of Hannah, right? So she never actually heard language. They finally did rescue her at age 7 or 6 or so. She got to like a 2nd or 3rd grade level of language, never proceeded past that because she was out of her critical window of learning. If you take chimpanzees, it takes them off 6 to 8 years to teach you how to survive out in the wild. When people either kill them off because they want bushmeat or use their hands as ashtrays, and they try and take the baby, and because they want to have, think it's kind of cool to have a baby chimp as a pet. And then they think, well, now it's too big and powerful to raise, we're going to re-release it back into the wild. It'll die of starvation. You think, what's a chimp? You should know how to live in the wild. Mom has to teach you. And if you don't get taught in the first 68 years, you will never learn. That's why usually older animals have a hard time learning. So the old saying, if you teach an old dog new tricks, has a certain level of truth to it. It's just harder to teach them because their window is getting more and more narrow. Well, of course, yeah, but ours are bigger and broader, and I think it's one of the things we gained evolutionarily, and we sacrificed other things for it. But definitely language, first couple of years of your life, if you don't get it, you're not going to have it. That's why little kids have an easier time learning language. If you can learn 2, and learning 4 is not that hard compared to learning 2 when you're early. Now, if I only learn 1 language, and then in my 60s try and learn the second, it would be harder for me. My brain did not need to know how to make those language pathways.
That's why it's best to be able to do a bilingual child and just talk to them both languages.
Right, yeah. The more they can be exposed to, the better. All right, so let's look at the thalamus next, folks. Give it a really quick, short definition. It is a relay station for sensory information to go to the proper cortex. It is a relay station for sensory signals to go to the proper cortex. Huh? Sensory, a relay station for sensory signals to go to the proper cortex. Now, how many of you are aware that you're sitting on your butt right now? Until I just mentioned it, you weren't thinking about sitting in your butt, were you? I was falling asleep because John's boring. Well, think about this. How many of you are aware of the watch on your wrist, the ring on your finger? You're not, right? Because the thalamus says, here comes a sensation from my finger called the ring. Does my somatosensory cortex really need to be aware of this? No. So it doesn't send the message. It simply says what is relevant, what is not relevant. If it's not relevant, I am not going to allow it to go to the proper cortex. How many of you maybe were studying and there's a certain noise you heard that kind of drove you nuts for a while, but after a while you kind of just forgot about it? You didn't forget about it. It was the thalamus saying, it hasn't changed, hasn't gone away. It's not no longer a threat to me. Let's just ignore it from now on until it's brought back to your attention. That is the job of the thalamus, to send sensory signals to the proper cortex, and if you don't need it, I'm not going to send it. All right, hypothalamus. First thing that has a connection between the nervous system and the endocrine system. Connection between the nervous system and endocrine system. Remember, it has a thing right below it called the infundibulum, which connects to the pituitary. The pituitary is a part of your endocrine system. You guys okay?
Yeah.
All right. Now, we have a couple of different collections of nuclei in the hypothalamus. Remember, nuclei are a collection of neuron somas. Three major ones. One is called the SONs, known as the supraoptic nuclei. So know the abbreviation and the full name. What is its job? They produce a hormone known as ADH. That's their job, to produce the hormone ADH. Does anybody know what the hormone ADH does?
Anti-diuretic.
That's what it's named. What does it do?
It's not good.
Kind of in the
Helps
kidneys.
you retain water.
Yes, right? It's to help you produce less or smaller volume of urine. So it's the anti-diuretic. Now remember now, that means that the cells that make it are in the hypothalamus, but it works on your kidneys. So it's got to get there by blood. Another group of nuclei known as the paraventricular nucleus, the PVNs, again, know the abbreviation and the full name, they make another hormone known as oxytocin. Keep in mind, these are two hormones, and what we're saying is they are made in the somas of these neurons that are found in the hypothalamus. They will actually be released from the posterior pituitary. They're actually released from the posterior pituitary. You'll learn way more about that in the endocrine system. Anybody know what oxytocin does? It's a bonding hormone. What? To bond two pieces of wood together?
Like people to each other, relationships?
Yes, bonding relationships for people. So when you have a new romance, you have high levels of oxytocin to bond with that person. What else does it do?
Is it in order to breastfeed?
It's involved in breastfeeding in the sense of it allows for the contraction of milk from the glands. What else does it play a role in? Birthing. It helps to trigger the birthing process, labor contractions. So realize that it's coming from hypothalamus. It'll be released from the pituitary, and it has a lot of cool different jobs. One of the ideas currently being investigated, since it's also known as the romance hormone, is that when couples kind of get to that point where it's like the thinking is that oxytocin levels are beginning to drop and are no longer high for those two individuals. It's kind of noisy over there.
So would they, if they were trying to induce labor, would this be something that they would give you?
Yeah, they actually give you oxytocin to trigger the uterine contractions. And you'll be taught all about that in 242, at least if you take mine. And that triggers the hypothalamus to release even more oxytocin, so it causes more contractions, more hypothalamus, more oxytocin, more contractions. It's a jump start. Huh?
You also call it, oh.
Yes, but it's synthetic oxytocin. All right, then you have another one called the suprachiasmatic nuclei. Don't get that confused with Mary Poppins. All right? Suprachiasmatic nuclei plays a role in your circadian rhythms. That means these nuclei are talking to the pineal body, talking to the pineal gland about when it's daytime, when it's nighttime. And these are talked to by your eyeballs. So it's eyeballs to SCN, STN to pineal body, kind of a pathway. Now, this next one, ANS, really isn't just one collection of nuclei. But if you were to ask, where does the sympathetic nervous system come from? Where does the parasympathetic nervous system come from? It comes from your hypothalamus. That's where it starts. Then it branches all different parts of your body, which we'll look at in a little bit. So we have the midbrain, what's called the corpora quadrigemina. Remember, these are collections of nuclei in the midbrain. Corpora means body, quad means four. You have 2 superiors and 2 inferiors. That's how we get 4. The superior's job is to respond to visual stimulus. It's a reflex center to respond to visual stimulus. The inferiors are to respond to an auditory stimulus. I can't do this in this room. I can do it easier in one of my other classrooms over at Seattle Central. But if I were to drop a book on the table, how many would jump? Right? That's the inferior colliculus. Ever experience sitting or standing, maybe driving at a stop sign, and you stop, and something kind of catches your vision, you kind of look in the direction of whatever that thing was, right? That's the superior colliculus. All you know is that something moved off to the side, and I visually turn in the direction of that side. That's why you have 2 of them, one for the right side, one for the left. Then it allows you to actually recognize what you saw or what you actually heard.
Wait, so is that associated with fears? Like, because fears are more like prefrontal cortex, right? Or-
Yeah, this is just, first of all, if I'm sitting here and I saw movement on what the hell was that, then I look and go, oh, it's just David.
Okay.
All it is to make you turn in the direction of the activity. Then you can recognize what it is. And if it needs a fear response, then you can take the frontal lobe pathway. You just need to know first of all something was actually moving.
So just lets you know that something is there.
Yes, but no definition of what it is. That's what you have to look at and go, oh, that's shape, that's sound, that's David. That sense. Then you have the substantia nigra, a different collection of nuclei. Substantia means substantial, means big. Nigra means black. So it's the big black body in the midbrain. It produces dopamine. Dopamine helps to inhibit, to stop unnecessary skeletal muscle activity. Produces dopamine to inhibit or to stop unnecessary skeletal muscle activity. So people with Parkinson's will have low levels of dopamine production from the substantia nigra. Certain pattern of flesh is going on. Okay. This is just for you to kind of put a context to where they are actually, right? You have the superior colliculus up here and the inferior colliculus over here. And we're not worried about the red one whatsoever. Then here's the substantia nigra, kind of on the same level as the superiors are.
So you have 2 substantia nigra?
In a sense, yes. Because remember we showed you that in lab where it's kind of a horseshoe-shaped pattern, in a sense, with a left side and a right side to it. It's right above the central canal. And that part called the tegmentum. All right, pons. It is a relay station for signals to the midbrain and cerebrum and cerebellum. It's like a big, gigantic, grand central station. Kind of like an overgrown sized thalamus, so it sends signals to all parts of the brain. You have 2 patterns of neurons, or what are called tracks, that run through the brain and the pons. Anytime you're about an ascending track, that means the signals are coming up to the brain. Those are sensory signals. All ascending are sensory. All descending are motor signals. And they all have to pass through the pons.
Are there any places in the brain that can kind of get bottlenecks or anything like that? I mean, we were talking about
So,
speed earlier,
what do you mean by bottleneck?
well, if you like running too much, stimulus through it, it's like with something like the pons, you have all like a whole bunch of stimulus kind of coming into it.
The pons, no. The thalamus, maybe yes. The pons is more like it's a corridor. Where I happen to find the fibers that, when I'm touching this wooden platform, an ascending track goes to the pons, but I can also feel the position of my arm. So a branch that goes to my cerebellum for my posture, another part goes to my primary somatosensory cortex, and Another part goes to my hippocampus for my memory. And this is more of the actual corridor. The idea of getting like overwhelmed with what you're thinking of would be more of association areas and the interpretive center and the thalamus itself having signals being all screwed up or coming out of the proper pattern, but not the pons. This is more of a place where I'm watching railroad tracks cross the road. That's the pons. But it doesn't actually do any interpretation. It's just simply where the fibers pass.
Does when a signal slow down at all, that would definitely.
No, I don't think so, no.
Shoots right on through.
Right, and even though it does have to have a pause, most of the signaling you're thinking about is no slower than 0.2 of a second. And that's our fastest response rate. So that would be the only problem, part of the delay would be that much. But overall, there wouldn't be any miscommunication, any confusion. It is simply more of just a place where neurons are passing through. But to interpret or to send signals or to receive and then relay them, that's what the interpretive center is and the thalamus job would be. So there you could have your idea of confusion, short-circuiting, or overwhelming take place. Now, in this next part, I want to put a little asterisk next to this. How many of you have the new McKinley Anatomy and Physiology book where the guy has the bicycle helmet on and the wheelchair? All right. In his chapter about respiration, he is going to say something that's going to be the complete opposite of what I am going to tell you. And he is the only author that says the complete opposite of what I'm going to tell you. He might be right, because he does say, in a little bracket in respiration, up until now, physiologists have thought just the opposite. But he didn't footnote it. He didn't reference it, so I can't figure out where he's getting his information from. So he might be true. But I've got 16 other books and a 2016 respiratory physiology book that says just the opposite. So what I'm telling you now is going to be exactly the opposite of what you read in this book. Okay? And that is that in the pons are two nuclei called the apopneustic pneumotaxic. Yeah, he agrees with that. What I'm going to tell you is that these two nuclei, groups of nuclei, are going to alter the normal breathing pattern. These will alter the normal breathing pattern. He's going to claim or state that they initiate the normal pattern. And he might be right, but he has no proof of it, and no other book agrees with him. So put a little asterisk and just say, I'm going to learn what John says. I'll vomit that out on the test. But just be aware that it might be proven correctly in the next 2 or 3, 4, 5, 10 years from now. So apopneustic pneumotaxic will alter the normal breathing pattern. They are two groups of nuclei found in the pons. How they do it, what they do it, we don't care. Okay. Just they do it, because it's complicated. This is just to give you a visual of where they are found in the pond. So you can anchor the fact that they exist in the pond. I'm not going to have a diagram that says name which one is which, okay? But I like visual representations. So there they are. Yes, the pneumotaxic is more superior to the apopneustic. But now we want to get down into the medulla, in that area. And in there are a lot of different groups of nuclei that have lots of different functions. One of them is known, or they're all kind of collected what's called the reticular formation. And that reticular formation is this thing, right, this gold thing. If you look at it, think of it as a mine shaft or an elevator shaft that goes from the midbrain through the pons, all the way through the medulla. And it's just a place where we have learned are lots of different nuclei, such as the pneumotaxic and apopneustic. They're partially in there. Your idea of the reticular activating center is found in this reticular formation. And it's just a pathway, a region that runs from the midbrain through the pons to the medulla that has lots of different nuclei. Some of them are such as what's known as the cardiovascular center. Cardio for heart, vascular for blood vessels. This will change your heart rate and the diameter of your blood vessels. It will change your heart rate and your diameter of blood vessels. So if you need to vasoconstrict, it's going to be coming from this part of your medulla. If you need to increase your heart rate, this will have sending signals to your heart to do so. It also plays a role in what I'm going to explain as the respiratory rhythmicity center, which is your normal breathing rate. This is where the signal comes from your normal breathing pattern. There are two groups of nuclei, one called the DRG and one called the VRG. The DRG stands for the dorsal respiratory group. That's not going to work. So dorsal respiratory group, and V stands for ventral respiratory group. The dorsals are involved in inhaling, and this is relaxed. And the ventrals are for forced breathing. So otherwise proven, let's memorize it this way. But these are the two conversations that the new book says are just the opposite. So right now you're going to learn that the dorsal respiratory group is your normal, relaxed breathing center. If you need to breathe faster, that becomes because of the ventral respiratory group. And then the apneustics and pneumotaxics, they modify this behavior. They cause them to change if they need to change. Again, just pictures for you to see them. I'm not going to have any diagrams, and also you can realize there's lots of nuclei that we're not talking about. But if you need them as a reference in the future, you can use this slide to show you. But there you can see the respiratory, and there you can see the cardiovasculars. So you can realize that they are in the medulla. And they're part of your autonomic center. You don't think about controlling your heart rate or your blood vessels or your breathing rate. All right, cerebellum is for motor coordination, being able to control the activity of your skeletal muscles, both in a voluntary and an involuntary way. So maintaining posture, balance, movement. This is probably where we get the idea of having motor memory, but really, or muscle memory. Your muscles do not have any memory to them. What you have is a specific pattern of using them. Anytime you'll learn a new motor movement, like playing an instrument or a new song or a new dance or a new sports move, those signals are laid down from the cerebellum. Remember the proper pattern of muscle activity to make those muscles work. That's the idea about having learning fine adjustments to movement. And then they remember that pattern, which we interpret then as your muscle memory. You just know which muscle to contract for how long, for how much force. Your sense of body posture comes from the cerebellum. If you close your eyes, you can envision how you're sitting right now. If your arm is folded, your chin's on your hand, right? You can feel that with your eyes closed because all those signals are going to the cerebellum, so you know what your postural position is. If you guys get pulled over and drink too much, it's one of the tests that they do. Right? Close your eyes, right? Can you maintain your balance? And then can you do this? Right? Oops, missed. Right? But that's because I should know where my finger is, I should know where my nose is, and being able to bring my finger to my nose is the job of my cerebellum. And it's quite easily affected with alcohol. One quick little tidbit. Let's just back up for a quick second to your medulla for a moment. And we have the cardiovascular and we have the respiratory rhythmicity center. You also have, just for information, Like your swallowing and cough centers are in the medulla. So if I have an uncontrollable nighttime cough, what am I going to do? Get some NyQuil, right? So I can inhibit my cough. Well, why do you not want to guzzle the entire bottle of NyQuil? Why is it dangerous to go past the normal required, what is it, half a cap every 4 to 6 hours? Is if you have your breathing center and one of your heart centers in the same area, they'll be influenced by the same drug. And you will literally cause your breathing to stop and your heart rate to go to an arrhythmic pattern. Because the nuclei that the drug is affecting for coughing is in the same neighborhood of tissue. And it has the same effect on them. Oh, that's it. Shoot. All right. That's it for the night. All right. Just a few minutes short. No sense in starting sensory neurons. All right. I'll just go over it on Monday. All right. So we will see you guys in the lab in about 10 minutes.
Is it the one that you passed?
Yep. Uh-huh. No. It's only taking a half an hour to go through that.
Are you posting?
Uh-huh.
Just for a little bit. And get caught like straight in the middle, very clean. So you can see like exactly like a bone. Yeah, it's pretty nice.
Straight down on the.
Like he's gonna show you like if this is like this is the shaping, this is like the point. You just cut from there like so it's like people cut, so when you cut it, it's gonna be clean, so you can see like the heavy cut inside.
Oh, nice.
We took pictures of that.